check. Oh, yes. All right. Okay. I think we're getting there. We're really, really close. Reorganize my screen. Oh. All right. We're ready to go here. I'm going to do last content lecture of the semester here. My last lecture as well. We've got one more coming up with us here, and that is Tuesday's review lecture, final exam review by Dr. P. And then there's going to be a student-led, student staff members. They're going to do a review. That's going to be after. I don't know. We'll have to check Piazza for scheduling on that one. But that's what we've got left coming up for you. Today's lecture is a bit of an add-on. This computational geometry lecture isn't on the final exam, so this is content that's just additional stuff to help edify you. You'll be better off for the future, especially if you run up against anything that's got some visual sort of graphic component. Some of these things are the good ways to think about things, and some of the basic equations and things that go into solving problems like this. So it is a later added lecture. I think we picked it up about 2 years ago. And since we've added this lecture, I would say about half of the time, yeah, Cindy, there's a 0 there. So about half the time this lecture doesn't even get included, because if we've got a snow day, we end up losing a lecture day, this is the one that gets booted. So I've given this lecture the fewest number of times. It's still the one that I'm the clunkiest at. I don't feel really comfortable with the narrative that flows through it as of yet. So apologies if this isn't top notch, but this is always a struggle lecture here for me. So I'll give some stuff out of it, and then we will call it after that. All right, that sounds good. So we've got some examples here of computational things here. This one right next to me here, this is from something called a KD tree that allows you to sort of partition data points along X and Y axes. And so if we think of this as a two-dimensional surface, and we think of a collection of ordered points that you can sort of put into a binary search tree for 2 dimensions. It's kind of how a KD tree works out. And then there's just some intersection stuff in terms of dealing with polygons. And on the far side way over there, we see some 3D mesh action. So it looks like a picture, but if you look closely, you can see sort of those white lines, and those are projections of horizontal and vertical slices there that divides this up into smaller elements. And this is how we can sort of describe a 3D object or even a 2D object with these 2D or 3D meshes. We'll start out with some computational geometry overview, just get some basic things out of the way, and we'll look at a few other things after that, and then we'll call it a day. So a lot of the things that we've done so far in this semester, everything actually, has been all sort of text-based as we deal with text coming in, text being processed, text going out. Sometimes, however, though, when we're starting to deal with non-text-based information, we're talking about graphical information, we have to figure out how we're going to represent that. And one of the first ways we do this is just the way that we look at it physically, and physically we're usually on some screen or other, and so we're looking at raster graphics. And raster graphics are something where they've taken the areas and divided it horizontally and vertically, and then the old machines used to use a electron shooter, and it would shoot things out in rows, and each particular place where it was trying to put some data in there turned into something called a picture element, which they just shortened to call it pixel, and that's where we get pixels from here. So in this case, we would take our images and turn it into a bunch of these smaller little one-color dots. And so you can see some examples of that here. If you start trying to store something in a file, it's very similar to the way that things are thought about when we're doing screen-based graphics here, because Everything that we're putting on a screen has a particular pixel at a particular location. If we were to store the data for one of those pixels in an array sort of style in a file, we would have the same sort of thing. So most of the time, these pixels, or even something that we look at in an image, whether it's a printed image or on the screen image, we can think of that as having some color for every small area. And this color is usually an RGB thing. Sometimes there's another color family used. It's called CMYK. The RGB, of course, stands for red, green, blue. CMYK stands for cyan, magenta, yellow, and black. CMY, and the K is for black. Not to be confused with the B for blue, so that's why it goes CMYK. So that's a way to do it, but if you take this and you say, well, each location has some amount of red in it, and we can store that in 1 byte. And then there's also some amount of green at that same location, store that in another byte, and some amount of blue at a location. Now we look at these 3 values that run from 0 to 255, because that's how much information we can fit into 1 byte. So you can think of the 0 level of red being absolutely no red at all, whereas the 255 level of red would be full on, we can't get any redder than we have here. If I pull on full R, full G, and full B, 255, 255, 255, that's going to give me white, whereas 0 and all of them is going to give me black. So all of the colors that we see on the screen are some combination of RGBs in this way. If I'm going to store some image then that could fit on a 1080p screen here, 1920 by 1080, just having those 3 bytes per pixel for every one of those pixels ends up with each one of these images well over 6 megabytes. So that's a fairly decent file size. But then as we look at other sort of high-res camera images, you can see these 27 megapixel dumps from some of these really nice cameras, and even larger than that. And then you get into some images that are stitched together, larger copies of other big high-res images. So we've got a lot of data here, and when we're taking something that's bitmap style, because every location is sort of prescribed as in what color's there, when we want to do things like zoom out, that's pretty easy. It's just like backing something away from you. But then when you try to zoom in, when we're trying to do that, as we sort of zoom in, we're starting to look at things that we can see there, and you can see sort of the pixelation that's going on there when we look really close at this 3 here. If that was something that was on a small device and it was, you know, maybe about that size instead of being this tall, that would look like a really smooth 3. But as you get closer, you can start to see those pixels. Right? Our alternative then is to not store things by pixel, but to store things with vector graphics. And in a vector graphics, the storage is more like, how do I compute this image, as opposed to how do I recall different parts of it. So when I compute it, I say, well, I've got this black bar you can see on that other side, that bottle of ice cream-based soda over there. That's supposed to represent a vector graphic there. So you say, well, I've got a black bar that goes across this way, and it's black, and it's about this thick with relation to the overall image. So then what happens is when I want to zoom in, the viewport has changed, and you can say, well, if this part of the viewport was just that section of the bottle now, if we recalculate where that black bar should be, we can get a nice crisp bar. So if that label on the bottle was vector graphics, you can see here that when we zoom into 7 times magnification, you can still see the text and the black line just as clear as day. Whereas if it's bitmap and you start getting in there, you get this sort of activity, right? So I've got this small little smiley face icon there, but you know that as you blow something up that's bitmap, as you blow that up, the computer then has to start making information up because there isn't enough information there to really make that picture be that size. And so you see the pixelation that's gone on there. But vector graphics don't do pixelation because they just recalculate at whatever viewport that's given, and it gives you this real clear, sharp thing. So a couple of different tools that you can look at for doing that, a couple of sort of open source editors that deal with these 2 graphic formats is GIMP. That's one of them. So that's the GNU image manipulation program. That's a knockoff of Photoshop. So Photoshop is a bitmapped based thing. And then there's an Adobe product, I forget which one it is, but the knockoff for that is called Inkscape, and that's an open source project that does vector graphics. And you can learn tons about those things just by tracking down the YouTube if you ever need to do any image manipulation stuff. So those are two real world examples of some of the stuff that we're going to talk about here. We talked about the size of images in terms of what they would take memory wise. We looked at all of those pixels. That 1920 by 1080 image is somewhere in the neighborhood of 6 megabytes. Then we start thinking about how do we compress this so that I can save some space. There's a couple of different approaches to compression. There's lossy compression and there's lossless compression. So in lossy compression, what's done is an algorithm has decided what features can I sort of ignore? Where can a little bit less of the color change not be noticed, right? So if you think of color sweeping through some red to blue, for instance, and there's really fine gradations across there, it looks really smooth. But what a lossy program might do is it might take sort of, instead of having it be a real smooth transition across the horizontal version of the screen, it might take it in sections that are about this wide, and note that, you know, if I've only got 4 of those sections, you might not notice it quite as well, but you get the idea that it's going from light to dark on the pass there. And so you can see this very, very famous image here of a model named Lena. So this was the image that the people that were doing JPEGs, this was the one that they used. And it's a bit of a controversial image. This was a shot from a Playboy shoot, and they used that, and they kept using that to refine the JPEG standard. She's totally okay with it, by the way. You can go read the article out there about her. She was happy to be that person. Not to say that that's a thing to be dealt with, but just as it gets brought up here, I don't want people to be misunderstanding what's going on there. But you can see here the original image at 12K, then using some lossy compression, that one in the middle has 85% less information. And you can almost not tell the difference. Some of the things in the face, the cheek area, aren't quite as sharp, and also in the hat, they're not as sharp. It's hard to see at this size, but the one that's on the far side there, this one's even more highly compressed. And this one's got sort of just about 3-4% of the total file size of the original. But that's because you can see that instead of having a bunch of different colors across the cheek there, now we've said, well, it's kind of light up here, and then it gets a little bit darker down there. And if we take these larger blocks, and that's how this compression works, it just takes areas. Instead of having a pixel for every location, it says, well, I've got a rectangle that's this size, and everything inside of it is that same color. So I can then do a compression there. And so this is an example of lossy compression, because we've said we're going to forego some of the details of this image. We'll lose some image fidelity just because it saves us in file size. On the far side, that's something more that you're going to see in sort of a GIF file. Oh, I said that wrong. It's not a GIF. It's spelled GIF, but it's actually pronounced GIF. So in a GIF, you're going to see things like that work really well. The GIFs for the GIF compression are things that are not images, but more drawings, right? So there I've got sort of a big white background and a black line that goes through it. So if I were to store that, you can see that even just saying I've got 2 colors now in this image. So rather than having each pixel represented by 24 bits, right? There's a red 8 bits, a green 8 bits, a blue 8 bits. So I can just, with this image, since there's fewer colors, I can represent every pixel with just 1 bit. It's either black or it's white. So already I've compressed this by a size 24, right? That's pretty nice. So you can see why flat backgrounds and sparse line graphics compress really well, even in a lossless version. So in this case, I don't have to lose anything if I say, well, I know exactly where every pixel would be black, but instead of having it be represented by 24 bits, I can represent it by 1 bit. And vector graphics compress even better because we've got sort of this formulaic way to generate an image. So as we look at being able to sort of take some image and maybe you wanted to put something on the side of an arena there, or a stadium photo, right? You would take something there and you want to blow that up. You wouldn't want to see pixels in whatever thing you're putting on the side of the big house. So those images have to be able to scale in a better way. So in that particular way, you would think of anything that got converted to a vector graphic, that file size is fixed. It's never going to get any larger, no matter how large you print the thing. So you can sort of get almost near infinite feeling compression as you feel like you're rounding down, though. You know, if you can take that thing and put it on the side of a building and still have the same file size because it's a vector graphic. So we get a lot of good compression out of vector graphics. On to geometry. Let's talk points, segments, and lines. 2 dimensions and 3 dimensions will mostly just be covering 2D stuff here. Adding that third dimension isn't a whole lot more work. It's just a little bit more math. So as we talk about concepts in this lecture, it's just getting that 2D concept is pretty good there. So we'll have a point that's an XY ordered pair. One way to define a line segment is to use 2 distinct points. You say I've got an X0, Y0, and a X1, Y1. So with those 2 points, I can define a line segment, the thing that connects them. If I'm looking at a 2D line, now this is something that isn't bounded by those 2 endpoints. It just goes off to infinity there. So as I move to a different portion of the image or the viewport, you'll still be able to see that line. Even if I scroll off, I can still see it going, scroll some more, it still goes, and so on. But just like geometry, we can represent our 2D lines in slope-intercept form. Y is equal to mx plus b, or in this case, it's kx plus c, where I've got this slope that's k, or m if you were doing it in algebra class, and on the far side, then I've got my y-intercept, which is what happens when x is equal to 0. All right? So I can use a segment, of course, to define a line, because the segment is just a portion of that line. It has some slope, and if you were to extend that segment, it would eventually hit the y-axis, and then it would have a y-intercept as well. So if I've got 2 points that aren't the same, let's see if we can find the slope and intercept from that. It's pretty simple algebra. Hopefully you can have remembered doing this one in prep school here, right? We've got y equal to kx plus c. In both of these versions, y sub 0, x sub 0, and y sub 1, x sub 1. So if those are 2 points, I want to figure out the line that joins them together. I can just set those, solve both of these 2 equations here for c, set them equal, and I end up with something there that I can solve for k. Ends up being this fraction where it's y0 minus y1 over x0 minus x1. There's my slope from 2 points. You should remember this. High school wasn't that long ago. Then I can plug that, once I've got k back in, I can plug k into either one of these and figure out how to get that c given the one of those x, y pairs. So different segments may define the same line. That's important to note, right? If I've got 2 points, I can sort of break that up. And there you can see if I've got a line segment between these 2 fingers and a line segment between those 2 fingers, they're on the same line. But line segments, because they have endpoints and they don't go on infinitely, they may or may not be the same line. They may or may not intersect, even though their lines would intersect, or their lines may definitely be the same thing. When we're dealing with line segments, we have to make sure we understand that there's limits to these things. And the other thing that's going to be pretty important is to use floating point variables, or floating point values, to handle these slopes and intercepts, because we can very easily represent the points with integers, as we did in Project 4, and get a lot of work out of that. But then if we're trying to connect these things, it's not going to work with just integers. So we'll be using doubles or floats, just not ints for those k's and c's. This set of information is about geometry transforms. Here we're going to take some collection of points or line segments and modify them all in the same way. One way to do this is sort of by shifting or displacing a point. I can use some input vector, which gives me some x and y component to move any one of these points by. So you see here that x comma y gets modified into x plus dx, y plus dy. So this is something that I can use to move or displace points. I can scale. Here this is going to be a multiplication, and in this case this is just a single a single axis scaling or stretching. So all we've done is multiply x by some constant c. This one's greater than 0, so it does sort of stretch it. If you wanted to compress it, then you would just have some c less than 1, right? That would make it smaller. So that should be a 1, not a 0 there. Yeah, sorry about that. Mirroring, all we're doing is changing an axis here. X turns into the opposite of x. That's a pretty straightforward one to understand. This one is a bit more mathy if you want to get back into that geometry class. We really have to deal with sines and cosines here. But I've got this rotation matrix, and I'm going to use cosines and sines, and to set up this rotation matrix, I've got some angle that I'm rotating this point by. So if xy is my point, I want to rotate it by theta. All I have to do is feed those xy into a multiplication. This is a matrix multiplication with this rotation matrix where it's a cosine of theta over the sine of the theta, the angle I want to turn by, and then in the other column it's minus sine over cosine. You do that sideways multiplication thing. We really lay the x and y over the top of that, so you see that x times cos theta minus y sine theta, that's my top component, and then the bottom component is when I take that xy and lay it over the sine cosine, and so that's where you see x sine theta plus y cos theta. So you can use this for transformation. Anytime you're trying to do something with graphics or designing something that's visual, you may use some things like this. As we move forward, we're going to look at some basic geometry questions and set up some of the answers to all of these. Will have some answers set up for them. Some will go all the way into it. Some you'll have to work a little bit more on. But it's just to give you the idea of what's going on here. So given two lines, let's see if they intersect. Can I find where that intersection point is? That's something that should be pretty easy to figure out. What about 3 points? How do I know if they're collinear? Do they lie on the same line, right? If they're not on the same line, then they form a triangle. How do I find the area of that triangle? Then another one that ends up being pretty important as we start dealing with polygons is, given 3 points A, B, and C, if they're not collinear and they form a triangle, is that triangle going clockwise from A to B to C back to A, or is it going counterclockwise from A to B to C and back to A? So it'd be nice to know this is going to help us with some of our other things. Another question, given a point P and a line L, do I know if that point is on the line, right? That's sort of the same sort of 3 points collinear thing, but when we're talking about 3 points, that's looking at really like a line segment and a point, or how do I know if they're all on the same line? But if I've got some line now, remember a line is just a slope-intercept, so it doesn't have additional points. It's just going to be going on and going on. How do I know if a point is on that line? If it doesn't lie on the line, what's the distance from this point, the shortest distance from the point to the line, and where on the line is that shortest point closest to? As we look at other things like a collection of points, and if I've got a collection of points, how do I bound them? How do I put a box around them? So if you were to say some of the stuff that we did from Project 4, there's a bunch of vertices, there's some box with a lower y and an upper y, a lower x and an upper x, that all of those points fit inside. How do I calculate those bounding boxes? What happens when I go into 3 dimensions? If I've got this whole collection of points, how do I find the closest pair of points? And do this in n squared, or how do I get even better than that, right? Find the closest point n among a point A. So these are some basic questions. We'll look at trying to get some of these answers. We have a couple of different kinds of questions as we look at these basic geometry things. Sometimes I'll be dealing with small sets of information, like several points or lines or segments. I'll be doing that, and I don't really have to worry about my algorithmic complexity because the numbers are so small, and I can just use my simple formulas or, some basic logic and figure that out. And then in other situations, I'm dealing with really large, right? So even though this collection here, there's a collection of them, just because it's so small, we think of that as several here. Whereas here, when I'm talking about collections, here's where n really matters. I've got so many points and lines that I need to do this efficiently in terms of n. Sometimes we can use our simple formulas. Many times, other times we're going to say, well, that's still too much work. I'm going to try to find a way to apply something that's a little bit more finesse. Before I end up this segment, we talked about using floating point values. One thing that's important to note, that the way that the IEEE float standard works, the way that the floating point value is actually stored in memory is not exact. It is an approximation. And this is because our floating point numbers are base 10 and the way that we put things in memory is base 2. So we've got an approximation there, and so this is where you get some rounding error. And I know you've done some math where you multiply something, divide something, plus it back in, you should be getting the answer is 4. But instead of 4, what do you get? You get 3.999999998. Like, okay, and we all know from early calculator learning that that really means 4, and so we just make that leap ourselves. But when we're doing this in a program, we have to say we can't do floating point comparisons for equality because we never know when that's really going to be good. So we didn't really mess around with this too much in P4, but the really safe way to do these comparisons with floating point values is to use an epsilon. And this epsilon is just a small value that we know that is sort of like larger than our rounding error would be, right? So if I take something like this where I would normally be comparing A equal to B, works great with integers, but if I've done some math on one and I've entered another one, it could be a 4.0 that I entered, and after the math, the answer was 3.999999998, and I say, well, are these two things equal? It would say, no, they're not equal. When in reality, because of what has happened, they should be considered equal. So instead of doing something like that direct equal comparison, we should be doing something here with an epsilon, right? And that epsilon is a small value, like I said, that's going to be larger than my rounding error could be. So then if I take that FABS, that's floating point absolute value, I'm going to subtract A from B, and this might give me a negative number, it might give me a positive number, but if I put it in FABS, and I'm sure I've got some positive value. And if that is less than my error, my epsilon there, then I can say that they're close enough to be equal. So this is how we should be doing floating point comparisons for equality. It's easy enough to figure out how I might want to do this. For inequality, I still have to use that epsilon. I've got to do some approximate comparison though now. Instead of just looking at A directly versus B, now I'm going to say, what about A versus B plus this epsilon, or A versus B minus this epsilon, to see that I'm in this area where I'm getting close enough, and I want to make sure that I am definitely still less than that value. All right. So that's the overview. We'll talk about a couple more topics. Up next, we're going to talk about points and lines. But as we look at how do I think of these composite geometry objects, there's a couple of ways that I can do this. Here, sort of the examples are a point set. So you can think of sort of a galaxy really as a collection of points. Whereas over on the other side, you see the state of Michigan map. That's a collection of polygons, or at the very least, a solid figure. So as we start to represent geometry objects, sometimes we think of them as points, sometimes we think of them as polygons. And here you can see some images that are made up of these meshes. And so these meshes are all a bunch of triangles. So if you look into how graphics cards work, high-end graphics cards that help you play the really cool games, they're all about how many triangles the things can generate, because they make meshes out of triangles. And so something in 2D here is easy to figure out what's going on there. But then as we see those three heads over there, that's all the same head with different degree of triangles there. That's all made up of a bunch of triangles. And if you can sort of display a triangle with your graphics card, then you can make this mesh look like something. And the finer the mesh is, the more smooth it gets. So we can see three versions of that with smaller and smaller 3D meshes. This is just an application of doing some of this lines and edges sort of thing here. This is solid modeling using CAD, computer-aided design, computer-aided drawing, computer-aided drafting. I never really knew what the D stands for. I think it stands for all three of those things, whoever's using it. But this is a CAD program. You see here a drawing of a vehicle, and it's just a bunch of lines that you put enough of them together, you get a surface. All right, on to points and lines. How about the intersection of two lines? So now I've got slope-intercept form. Remember, lines go off to infinity. So if there are two lines that I have defined, then I've got three possibilities, right? One is the lines are parallel, there's no intersection. Two is the lines are the same line, so they're completely intersected. Or otherwise, I've got intersection at one point. So if I've got these two lines and I want to figure out what is the intersection point, you see that the first thing I have to do is take their slope-intercept forms and then check to see if their slopes are equal. Because if the slopes are equal, then I've either got my parallel line or I've got my same line. So those are pretty easy to figure out, right? If my A is equal to my C, my two slopes are the same, and my B is equal to my D, my two intercepts are the same, then it's just the same line. But if the B is not equal to D, then they're intersecting the axis at a different location, and so what I've got is parallel lines there. However, now if I'm talking about some intersection, two lines that are going to cross each other, this is when I have the slopes are not equal. A is not equal to C. To find that intersection point, it's pretty easy. We just use our basic algebra. I'm going to say at that location y and x are equal. So I can say that same point y0, x0, when applied to both of these two equations here, y0 equals a times x0 plus b, and y0 is equal to c times x0 plus d. I can set those equal to each other, turn around, solve that thing for x, boom. Once I've got that solved for x, I can turn around and get that location there. And so this is how I find this intersection point, x0, y0. It's the place where both of these two equations are equal. Another way that I might get it, sometimes I'm given two lines as a collection of points, right? Or 2 points for each line. This is kind of like the segment version. But rather than just being limited to within my segment, I want to say, I know that these things have a different slope, so there's going to be some intersection, or if they've got the same slope, then I determine whether or not there's an intersection. There's not much difference there in terms of how I would get to that. As I do some algebra in there, it turns out to be just quite a bit more algebra, but we end up with something like this. So save yourself some headache and maybe a lot of pencil and paper next time you need to do this. Just go look for an equation like this on Wikipedia. You can see here that just given these 4 points, 2 lines, 2 points per line, I can determine where that intersection is at px, py. And here we find out that if the denominators are 0, then I've got parallel lines. That's that quantity there, x1 minus x2 times y3 minus y4 minus y1 minus y2 times x3 minus x4. If that goes down to 0, then I've got parallel lines, and so I won't have the full-on single point intersection. All right, so that was line intersection. What about segment intersection? In segment intersection, I've got now lines that don't go off to infinity. There's this segment here, and if I've got another segment there, that's not really an intersection. The intersection has to take place between the 2 points that define both of my segments. And one of the ways that we can do this is by checking the orientation of the triangles that get generated by these endpoints. So I end up with 4 total ways that this can happen when I've got 2 line segments, right? The 2 on the top here, you see those are the ones that actually have intersection. And then there's the 2 on the bottom, and they don't have intersection. So that's one of my ABs. And then the other AB is my left column here versus my right column, right? And in the right column, I've got 3 points that are collinear. And in the left column, I don't have any 3 points collinear. So I've got 2 ways that I can have intersection. One with 2 collinear points only, and then one with 3 collinear points. And then I've got 2 ways that I have no intersection. There's something with no collinear sets or 1 collinear set there. All right? So the orientation of the triangles here, as you try to imagine what's going on there, I've got sort of the red line versus the blue line, and then I'm also going to look at the blue line versus the red line. So if I take the 2 end points of the red line from P1 to Q1, and then I make a triangle with one of the endpoints of the blue line. So let's take the P version. So we'll go P1 to Q1 to P2 back to P1. That's a triangle, and you see that those points are sort of arranged counterclockwise. All right, let's go the other route. I go from P1 to Q1 to Q2 back to P1. Now I've got a clockwise triangle. So in this case, my red to blue is, the two triangles have different orientations. One goes counterclockwise, the other one goes clockwise. All right, let's jump over to the blue versus red, and I'll go P2, Q2, P1, P2. That gives me a clockwise triangle. And the other endpoint of the red is P2, Q2, Q1 to P2, and that's a counterclockwise triangle. So it turns out I know that there is an intersection of these two line segments if I can say that the orientations of these four triangles are alternate, right? If they're different. So if the red ones have a clockwise and a counterclockwise, and the blue triangles have a clockwise and a counterclockwise, then there's definitely an intersection in between there. All right, on the far side, you can see that I've got the same sort of thing here, but since I've got a collinear point there, I don't get a triangle out of that P1, Q1, P2, P1. They're collinear, so I get a line, but then I can think of that as sort of like if I've got a positive triangle or a negative triangle, that's my clockwise and counterclockwise, then you can think of that collinear as being a zero triangle because there's not really any area there. So then if I say that my P1, Q1, P2, P1, that's a zero triangle, versus my P1, Q1, Q2 back to P1, that's a clockwise triangle. So I've got a zero versus a clockwise. I can say that those are different. And I will have an intersection if I can say that both of the blue triangles versus red are different as well. And so I check that out, P2, Q2, Q1. That gives me a nice counterclockwise triangle, whereas P2, Q2, P1 gives me a clockwise triangle. So there I've got the reds are different, the blues are different. There's going to be an intersection. The bottom two examples, we can see the exact opposite of the things there. We've got something the same here. So what's the same here? The orientation of the blues to red. So if I start at P2, go to Q2, Q1 back to P2, I've got a clockwise triangle. P2, Q2, P1, P2 is another clockwise triangle. So because those are the same orientation of those triangles off of the endpoints from the blue to the red line, there's not going to be an intersection, right? And the same thing is true on the far side, even with the collinear points. You see that if the red line was a line instead of a segment, we would have an intersection, but we don't have an intersection in there now. So this is what's going on with these segments here. If I find the lines by those segments, if they're parallel, then I can say with the same slope, if they got just different intercepts, they're just parallel lines, I can always return false. And so the question here really is, the first question was, do they intersect, right? And then the second question is, if they do intersect, then find that point for me. And all we have to do is a project in there, we'll figure out where that is. How about collinear points? That was kind of important in that previous slide. We're trying to determine whether things were collinear. How do we determine whether these 3 points are collinear? Well, one way to do this is to think of them P1, P2, P3 as basically 2 line segments from P1 to P2 and from P2 to P3, right? So if I take those and look at them as line segment A and line segment B, I can do some slope intercept calculations, find those things. So I got a K sub A and a C sub A for the slope and intercept of the A segment, and I can do the same thing, a K sub B, C sub B for the slope intercept of the second segment. Now I figure out that they are collinear if they've got the same slope and they've got the same intercept. So that's another way to figure out whether these things are collinear. Moving on, how about measuring distance from a point to a line? We've got this function here, source Wikipedia. Go check this out. There's some good proof on how this stuff works and the algebra behind it. But if you need something like this, it's good to just be able to double back, find a formula, plug it in and get it. This is the sort of thing that the competition programming team either has memorized or they have a cheat sheet that has all of these geometric formulas. So they say, well, if this problem has me measuring distances here, you just sort of figure that out, right? So rather than having to do the derivation, we'd love to be able to just determine what's going on in the problem, look at a geometric sheet, and apply the formulas as necessary. So this one calculates the distance. We see that we've got something that's very distance formula-like. I've got a square root of a squared plus b squared in there. That's part of my line definition. And then I've got the line as applied to the point in question, the x0, y0. I take the magnitude of that, divide it by that distance calculation there, and we've got something there. If we want to find the coordinates, here's just the xy coordinate. We just plug those values in there, the a's and b's and c's from the line, plus the x0, y0 from the point. You plug that in, there's your point. Here's a minimum bounding box example. So I've got some blue points here in 3 space. You can see that I've got x, y, and z on all of those things. And this red box that's in there is the smallest box which all of those things fit into. So this is pretty easy to see how you might get that. As you look at each point, you're going to be looking at whether it's got a bigger x than any other x, whether it's got a bigger y or a smaller y or a smaller z. And so all we have to do is look through each point's x, y, and z. Or if I'm in 2D, it's just an x, y. I can find some bounding box of a set of points. Pretty easy to do if I keep my box edges parallel to my axes, because then it's just about the largest x or the smallest x. Largest y or the smallest y. I just look at each one. I can do that in linear time. I just look at each point, compare it to my minimums and maximums, and keep moving on. Usually, however, though, there's a smaller bounding box than one that's oriented with my axes. That's a little bit harder to find. Still possible in linear time, but it's not a trivial algorithm. So we would have to look into that. But this is just an overview. We're talking about various sort of geometric problems we might have. So that's points and lines. Some other questions that might show up here, like how do I find the closest pair of points? So given some collection of n points, I want to find the 2 with the minimum distance. It's pretty easy to just do an n squared version of this. We've done something like that already for this P4. We can just take every point, compare it to every other point, and find that distance there. Another way to do this is if I'm going to use in 1 dimension, I could sort these things. In 2 dimensions, you could use a divide and conquer algorithm where we take some left side and right side and we get this middle strip and start alternating directions and trying to figure out what the distance back to this center line, this S, is where this split comes in. So I've got some set of points on the left, some set of points on the right, and then I'll start measuring that out. So this is another algorithm that's used to find the closest pair of points. This one gets you something faster than that n squared there. We can use this x median partition. So I'll recurse on the left half, find the minimum distance, recurse on the right half, find the minimum distance. Or we could use this middle strip there, sort the strip by their y, and compare each point to some points after it, before it. So these are some of the things that you would learn if you needed to do these things. It's a good place to start looking for these algorithms. So we end up with this recursive sort of version as I'm working my way through this strip. And it's kind of like quicksort in that I've got 2 linear terms now, though, for partition and processing in the middle strip. So I end up with this n log n time. If we were to sort it, we would get something like n log squared n. This is not n times log of n squared. This is n times log squared of n. But this is the way that this algorithm is used to find closest pair of points. How about finding the closest point from n? We like to serve this up for a bunch of queries in the future, right? For some point, find this closest point among n other points, right? It would be sort of misleading if I thought about that in general, but I'm looking for the closest point from a collection of them. So if we're trying to do better than the obvious, which is just this n squared thing, we build some search index. And this should be bringing back some painful Project 3 memories, but that sort of thing is a very common way to deal with processing in computing, is when we know that we're going to be asking a question regularly, let's build some search index so that we can get to an answer there pretty quickly, right? So things like databases do things like that. Other geospatial stuff, internet network trafficking things, CAD and the like, do things like that. So that's points and lines. Next up, polygons. We start talking about polygons, we really start seeing shapes. We talked about triangles earlier, and I talked about sort of clockwise and counterclockwise triangles. So the clockwise test is going to tell me what the order of these points is. And that's good for triangles. It's also good for other higher order polygons. You want to know if I've given a list of points and they're sort of describing a polygon, are they going in a clockwise way or are they going in a counterclockwise way? So to start out at the fundamentals, let's just go back to triangle. I got these non-collinear points, so I know I've got a triangle, A, B, and C. If they turn counterclockwise, left, or if they turn clockwise to the right, that's one of the things I want to know. The other thing I want to know is, now that I know that they do form a triangle, what's the area of that triangle? And turns out I've got one formula that solves both of those things. And it's just some matrix algebra here, so we can plug some things into a matrix here, this 3x3 matrix, and you can see I've got each of my 3 points, AX, AY, BX, BY, CX, CY. So those are my 3 points, A, B, and C. They're XY components. And then in that third column there, just a bunch of ones. If I take that 3x3 matrix and get the determinant of it, fun linear algebra stuff, I end up with a value. And that value is going to be non-zero, right? Because we know that we have 3 non-collinear points. So I do have some triangle. What that value is the area of the triangle. But it's also a signed value. So sometimes it's negative depending on the order of the points. So I can use the same exact equation to calculate the area and to calculate the triangle orientation. So I say if it's signed and my triangle area comes out negative, obviously the actual area is a negative. The area is the absolute value of that negative, but that negative tells me that I'm going clockwise with a negative number and counterclockwise with a positive number. So that's going to be useful in this next section as we start trying to figure out how to find the area of a polygon. So looking at this thing, you say, well, I could take these endpoints with no intersections in there other than their endpoints and say the endpoints, endpoints. See that pronunciation there? The endpoints, endpoints. As I put them together and make this polygon, how do I find the area of this thing? It's not trivial when it looks like that. One thing you say, well, I can use triangles. I know how to get a triangle. We can do some stuff there. We end up with quite a bit of math as we're trying to figure out what the base of, let's say I could subdivide this T polygon by drawing a line between P2, P5. That makes one triangle on the left, and then P2, P4, and splits the remainder into 2 triangles. Now I've got 3 triangles. I can apply some triangle formula and get the sizes, the areas of these 3 triangles added together, and that's my total polygon area. Ends up being a lot more math using triangles than it is if I use trapezoids. Trapezoids, you say? Yes, I say traps. So here is a simpler polygon. It still would work with something as complex as the previous one, but this is just a lot nicer to look at. And we can see that we've got our vertices numbered, and in this case they're going clockwise, 0 to 1 to 2 to 3 to 4, back to 0. And so that 4 to 0 jump, because it's going to the initial point, is still considered to be like going in a increasing order. I mean, as 0 increases to 1, moving clockwise, 1 increases to 2, I'm moving clockwise, 2 to 3 is clockwise, 3 to 4 is clockwise, and 4 to 0 is clockwise because it's not contiguous. It's not 4 to 5, it's 4 to 0, it's back to the beginning. So this is a polygon with 5 points, and I can then sort of draw an x-axis below that and take each one of my vertices and draw a vertical line from that vertex to the x-axis. So now if you look closely, you can see a collection of 5 trapezoids. There's one that goes from 0 to 1 down. There's one that goes from 0 to 4 down to the x-axis. There's the 4 to 3 down. There's a 2 to 3 down. And so you get the idea. There's 1 to 2 over there. So this is 5 trapezoids. Okay? What's good about a trapezoid? It's really easy to calculate, right? This is just sort of like a triangular region up at the top on top of a rectangular region. So you can see that I've got my width times my height. That's going to give me the rectangular area. But then to get that triangular area, it's additional the 1/2 base times height thing. So this is what the area of a trapezoid looks like. It's just width times the 2 heights added together and then divide by 2. And why that's easy is when I've got points, as I'm talking about defining these polygons with a collection of points, it's easy to add a formula like this and say that area is just x1 minus x0 times y0 plus y1 all over 2. The x1 minus x0, of course, is the width, and the y1 plus y0, those are my 2 heights. Add it together, multiply, divide by 2, area of a trapezoid. Still concerned about why we're doing this? Next slide is going to make this all happen. So, if I can measure and calculate trapezoids really easily, then you can see that to calculate the area inside the polygon, all I have to do is add up the areas of all of those green polygons and subtract the area of the red polygons, and what I'm left with is the things that are inside the polygon that I'm worried about, right? So plus trapezoids minus trapezoids equals my total area there. That's pretty cool. And since each edge in my polygon is the top edge of a polygon, each edge in my polygon is the top edge of a trapezoid, I can do these calculations fairly quickly. The question though is, how do I know which edge is a green polygon and which edge is a red polygon? Have you figured that one out? Right, what are the polygons? Points are not in strictly increasing or strictly decreasing order. Well, that's kind of a prerequisite. If we're going to give you a polygon that has a collection of points, we're going to say that they follow each other. Otherwise, you have to add more information to determine what the polygon actually is, right? So you've got a collection of points and you don't assume that they're in order. When do you know when to jump forward, backwards, and whatnot there? So in terms of the way these things are going to be specified, you're going to get a polygon that has the lines, the vertices in order, one way or the other, clockwise or counterclockwise. All right, so as I move from left to right, I can see this, I encounter 4 first, and then I encounter 0. And remember, that does go down in value, but because it's going down from the last one to the first one, we still consider that as sort of a positive jump there. So this is an increasing from 4 to 0. This is increasing from 0 to 1. There's an increasing from 1 to 2. So those are all my increasing edges there. So those are the ones that give me green polygons, right? As I go from left to right on the red ones, you see they go from 4 to 3. That's a decrease. I go from 3 to 2. That's a decrease. So those are the ones that end up as polygons I want to subtract. So if I add the positives and subtract the negatives, I end up with the yellow there on the far side. All right? So you can see there that if I take each one of those as a +1 of that area, and then the white part, of course, is going to be ignored, and I've got a -1 in the red stuff. I put all of that together, and I end up with my final answer there, which is the area of that yellow polygon. All right? So if I look at these formulas here, it's pretty easy to see that those trapezoid areas are just right there. If I wanted to get unsigned areas, meaning that all my areas were always positive or 0, then I would sort of twiddle around with that x. because when I'm going from left to right, I want to have this sort of be a positive number if I'm going for unsigned area. So the green trapezoids have all my x sub i's are less than my x sub I plus 1. So as I move to the next point, I can say that the x of the previous point is farther to the left, and so on. The red trapezoids are exactly the opposite there. So in order to get a positive value, I have to switch the xi and the xi minus 1. But if I apply the green trapezoid, the signed area there with the green trapezoid and the red trapezoid, then I've got the green ones is giving me positive values, and the red ones just automatically give me negative values. So I can just calculate all of them, add them together, and I've got the answer. You say, what about non-convex shapes? This one gets a little bit more complicated when we look at it, but the math works out the same. As I'm looking at my edges that go forward, I end up with some of them get double counted in non-convex shapes here. So you can see sort of the dark green areas are where that trapezoid has been added from more than one area, right? The same thing is true for my red ones that can be subtracted from more than one area. So the dark red is then a double there, but it works out, it still works out. So everything that's added in there as the things that I only want one copy of, I got 2 dark greens on that little band and the star there, and then we minus 1 from the red, and I end up with my final value there that I got that. So it still works. That's what I'm getting to there. All right. Another way to look at area of a polygon is called the Shoelace Formula, and that's just a different mathematical way. If you see what's going on in this area equation there, this is looking very much like some trapezoids, right? You've got that 1/2 times base times a height there, and as we keep adding them up, and we sort of, like, it's called the Shoelace Formula because it ends up kind of looking like this as we work our way through there. So we've got the plus ones and the minus ones and the plus ones and the minus ones, and as you do that, we end up getting the area of a polygon using this known as a Shoelace Formula. And we could do it in linear time, linear in the number of points there. So that's pretty cool. Much more, it's much easier to deal with than trying to figure out how to do this with triangles. New problem here. How about, is this point inside the polygon? So here we've got the polygon, you see it here, drawn in black and blue and red, and I've got this green point there. The question is, I can see this, but how do I program this sort of thing? So given some polygon defined by these endpoints in order, and some point P, how do I know if the point is inside the polygon? Turns out we can draw some horizontal lines. So if you can see this here, you can see that I've got this collection of points that are either inside or outside, and just drawing this horizontal line across, we get some additional information now. What is that information, right? How many lines in the polygon does this horizontal line cross? So starting at A, we see that it crosses none. Well, that's 0, but that's an even number, right? So if it crosses an even number of line segments, then we can say that it's outside of the polygon. So you see B there, B crosses those top 2 and then moves over and crosses the other top 2 for a total of 4. Even number outside the polygon. C is inside the polygon because it crosses only 3 of them. 2 across the middle and 1 on the side. We'll get back to D in a minute. What about E? E is in the dead center there. It only goes over 1 edge, odd number, inside. F is here completely out. We hit 2 edges, even number, outside. And then G, like D. How do we manage the G's and D's? Because they go through an actual vertex. So one way we could do that is if we can determine that it goes straight through a vertex, just ignore that connection, right? It's not really an edge, it's a vertex after all. We're trying to figure out how many edges we cross. So we can look at that D line, even though it goes through the vertex, we can say, well, it only goes through 1 edge. So that's an odd number, so it must be inside. Whereas G, because it's going through a vertex but not through any other edges, it's an even number, is a 0, so we say it doesn't go inside. Another way to do this, of course, is to use our epsilon. We can sort of do some wiggling. That's what it's called. Like technically, you wiggle it. So if I were to take this epsilon and add it to the y component of d, if I add it and it moves that d up just a little bit, so now it's no longer going through the vertex, but it's going through the edges, then you can see that instead of going through the vertex, I would hit 2 edges and then the third edge, and it would be there, right? Or if I were to wiggle d down just a little bit by epsilon, then I would only be hitting the far edge, and it would still be an odd number. So you can use epsilon here to help you figure these out rather than trying to figure out if this line goes directly through a vertex. Same thing with G. As I wiggle that up, you see that I hit 2 of them, so I'm definitely outside. Or I wiggle it down, I'm hitting nothing in the polygon altogether, so I'm definitely outside. All right. That's what I got on polygons. And that about wraps up the stuff that I'm going to talk about here today. This is our last lecture, and it's a bit abbreviated, but that's what I've got here. All right, so just got a text from Dr. P that I didn't get these slides posted. My apologies there. I will go post those here in short order. But we'll see you in office hours. And like I said, we've got one more lecture. That'll be the Dr. P lecture here on Tuesday, which is our final exam review. And then there is a staff-sponsored final exam review as well. So be on the lookout for information about that. All right. Well, I won't see you again, or you won't see me again. I don't know. I haven't seen any of you all semester. Just little circles with your initial in it, or the occasional mountaintop picture. But it's been a lot of fun this semester, even though we've all been locked inside our various places. Hopefully, we'll have a chance to connect here once we get back to campus. Next semester, maybe the semester after that, we'll get there. All right, take care. See ya.